from homework? Does anyone have homework questions? I think last time we assigned, I don't know, some problems like up to 19-ish. I think we might have skipped a couple in between, but right in that neck of the woods, Khalil?
I'm trying to think, like from the delta math that we did last class.
Yeah.
You do one of the polynomial long division.
Can we just, let's just do one of the homework problems because it's like still the same thing, right?
I don't have my notebook, so.
That's okay. I can just pick one. Does that work for you?
Yeah.
Okay. Let's pick, oops, it's the wrong spot. Let's pick like this one. Sound good? Does that look like what you're seeing?
Yeah.
Close enough anyways. All right, so let's start with the setup. So we're going to do long division. So my division bar. The denominator of the fraction is the number that goes on the outside. But if I look at the denominator on the fraction, I see x cubed plus x minus 5. I notice that I skipped something there. What did we skip? The x squareds. So when I notice that I've skipped a term, I'm going to include that and use like 0 x squareds. Now, for long division, we don't have to include that, but boy, it makes everything line up really nice when we do, and I highly recommend you look for those. The number that goes under the division bar is the numerator, and I'm going to do the same thing, and again, I notice that I have no x squareds. So just like the divisor, I'm going to include a 0x squared there. And again, we don't have to have that, but like it takes a lot of effort to make sure everything's lined up correctly. If you don't, highly recommend that you include those zeros when we do our long division. It makes life much, much simpler. Okay. So now I'm going to ask myself, what times x cubed gives me 4x to the 5th? What times x cubed gives me 4x to the 5th? Well, it needs a coefficient of 4, right? And to go from x cubed to x to the 5th, that needs an x squared, because the exponent has to go up 2 places. Everybody agree? So this number needs to be 4x squared. Once I've decided that, that's going to multiply to everything in the divisor. And then I'm going to write that number underneath. And then we subtract down, right? But remember, Mr. Kulik says, don't think about this as a subtraction problem. Distribute the negative and then do an addition. So when I distribute that negative, I'd have this. So now we're just adding straight up and down. So 4x to the 5th plus negative 4x to the 5th is 0. 7x to the 4th plus 0x to the 4th is still 7x to the 4th. 1x cubed plus negative 4x cubed is negative 3x cubed. 0x squared plus 20x squared is 20x squared. And then I'll bring the rest of this down. So far, so good. Now I'm just going to repeat and ask myself, what times x cubed gives me 7x to the 4th? What would that be? 7x. Great. Thanks, Avery. So we'll put plus 7x up here. And again, that distributes to everything in my divisor. And I'll write that underneath. Nathan, you doing so far okay? Okay. And then we'll subtract down. But remember, don't think about this as subtraction. Distribute the negative and make an addition problem. Oh, come on, you stupid machine. You can see the eraser on here, like just not erasing anything, right? Like, how frustrating is that? You stupid machine. Okay. Okay. Finally working. So 7x to the 4th plus a negative 7x to the 4th is 0. Negative 3x cubed minus 0 is 0, or is negative 3x cubed. 20x squared plus a negative 7x squared is 13x squared. Negative 8x plus 35x is 27x. And then we'll bring that 1 down. And then we'll repeat and we'll say what times x cubed gives me negative 3x cubed. Negative 3. And then again, distribute that to the entire divisor. And we'll write that underneath. We'll subtract down. And we'll distribute that negative through. No problem. Do you need a note for somebody? Slusser? Okay. Thank you. Yep, I'm emailing him right now. You're welcome. Thank you. All right. So we're doing that. What do we get? We get 0. I get 13x squared, 30x minus 14. So like that's my remainder. How do I know all that's my remainder? Well, the degree of the remainder has to be less than the degree of the divisor. As soon as you see that's less, you know you're done. So we'd write our final answer as the quotient plus the remainder over the divisor. And that's how we'd write our final answer. Nathan, does that satisfy you? Okay. I know it wasn't exactly a delta math problem, but it's like a 2-for-1, right? Good enough, and then here's a homework problem that, hey, you hadn't done that yet. Now it's done for you. And that's probably the hardest of those division problems from the homework, right? Those of you that have started, you're all looking at me blankly. Like, sure, if you say so, Mr. Kulik, I haven't started yet. I think it was. Other questions for me? Okay, let's get crack-a-lackin' here. We can finish up chapter 13 today. So in section 13.3, we started this last time, and all we did from chapter 13.3 last time was talk about division of two polynomials, right? We showed you long division and synthetic division. When can I use synthetic division? Could have I used synthetic division on problem number 19? No, why not? Great. So to use synthetic division, the divisor has to be in the business what we call monic. That means its degree is 1 and its leading coefficient is 1. Here, this is right away, since it's a degree 3 polynomial. We can tell we can't do synthetic division here. We have to do long division. And before we took this break to talk about these polynomial division techniques, we'd been talking about finding zeros for polynomials, right? So up to this point, the only zeros for polynomials that we found were ones that we could use, you know, like a greatest common factor and then some quadratic factoring to get, right? What happens if that's not going to be possible right from jump? What else can we do to try to get the zeros for this polynomial? That's what we're going to be concerned with for the remainder of chapter 13, is developing and filling out these techniques that we can use to try to find the zeros for polynomials. So we're going to add to our collection a couple of theorems that we can use to help. The first of those is called the remainder theorem. And what this says is that if I have a polynomial f of x and I divide it by the factor x minus k, the remainder for that division problem is the same thing as if I plug that k into f. So let's look at an example of kind of what we mean there. So this example says using the remainder, or find f of 2 using the remainder theorem. So f of 2 is like my f of k. So, and my f of x is this 2x squared minus 5x plus 4. So what I need then is an x minus k. So for this problem, my x minus k is x minus, what's k? 2. Good job, Lexi. So, okay, the division, or the remainder theorem says, okay, the remainder of the division problem is going to be the same thing as if I plugged 2 in for x. So let's see, you do x, or 2x here, so that's 2x squared minus 4x. Subtract down, that's negative x plus 4. To a negative 1, x plus 2, subtract down, and that's 2. So I should be able to say that f of 2 is equal to 2. And just to kind of confirm that, I get 4, 8, and then 4 more is 12, minus 10. That is indeed 2. Now, this is typically a lot more work than doing this, right? Ideally, we'd like to use the remainder theorem to go that way and somehow use substitution to replace division. Everybody agree with that? That seems like a much better deal for me. You guys agree? Yeah, that substitution makes seems a heck of a lot easier than the division. And that's exactly what we do. That's exactly what synthetic division is, right? Synthetic division is a substitution process that also accomplishes the division for us. So that's exactly what we're doing when we do synthetic substitution, is we're replacing the division with a substitution. In particular, if we're talking about trying to factor a polynomial to find the zeros, what specific value for our remainder are we going to be most interested in? If the goal is to factor the polynomial to find the zeros, what remainder would we be most interested in? Remainder 0. Yep. And why would remainder 0 be the one we're looking for? Because if we get a remainder 0, it meant that that factor, or that divisor, the x minus k in this case, is a factor, right? So the factor theorem just tells us, hey, if f of k is equal to 0, then x minus k was a factor. Big surprise, right? Let's just do an example to kind of show that. So I can just say, what's the k in this case? Should start there. So x plus 3 is my x minus k. What's k? Nope. Nope. Negative 3, right? Because what are we really doing? We're taking x plus 3 and setting it equal to 0. So that's like my k. So if I do f of negative 3, that does come out to be 0. You take my word for it. You type in your calculator and double check, but it's 0. It's just the mental math on that's going to be pretty crummy. 25 times negative 27, I just don't really want to do it, you know? I just like, no thank you. Oh, I'm sorry. That's just negative 9 times 25. That's doable. Negative 225. I don't want to do negative 27 times 6, though. I guess that's 162. I guess that's not so bad either. That's 225 minus 48 minus 15. And that is 0. All right, I lied. I did it. The mental math wasn't so bad. I got confused on which one was. I thought the 25 was on the negative 3 cubed, and that was just going to be a hassle. Now, what's the issue here if we do it this way? Well, we know that this is going to equal x plus 3 times something, but we don't know what that other something is, right? That's where doing the synthetic division comes in really pretty handy, because it accomplishes both of these two things. Now the process is a little bit more time consuming or whatever. There's my 0 remainder. But what it tells me then is these numbers right here tell me that -5 is the constant, 7 is the x coefficient, and 6 is the x squared coefficient. That accomplishes both, right? It tells me that thing is a factor, and it tells me how to do that initial factoring. Does that feel okay there? So that's why the synthetic substitution here, aka synthetic division, is so helpful. Is because it does both of those parts for us. It does the division, or does the substitution, and it does the division at the same time. And woo, that's pretty handy. Okay. The question here then remains, we're again still trying to get to zeros. We're still trying to build that out. Do another example here. We've been talking about this synthetic division here for a minute. Let's do that again. So it says here to use synthetic division to evaluate f of -5. So that's like your factor, right, that we're checking. So synthetic division, the -5 still goes on the outside. And what do I notice about my polynomial that I'm dividing that I have to be really careful about? I go x to the fourths to x squareds. What did I miss? X cubes. You must remember those zeros for synthetic division. It is unrecoverable mistake if you forget to put the 0 there. You will not get the right answer, and there's no way to notice right away that you didn't get the right answer. You are just plumb stuck in a mess of your own makings. That's what we want. So you know f of -5 is equal to 2332. And that was probably going to be easier than trying to plug -5 in up here and evaluate that by hand, right? -5 to the fourth times 4, yuckarooskies. I'm not too interested in that. I mean, I can mental math it out, but I'm a math teacher, right? If you try to mental math it out, it's a tough one. All right. So what we're seeing here is, okay, if I know some factor for my polynomial, I can do a synthetic division to get at least a partial factoring of it, right? Maybe the 6x squared minus 7x or plus 7x minus 5 can be factored a little bit more. Maybe it can't, but at least I can get like some factoring done with just a synthetic division. Everybody see that? The big open question for us is, how do we come up with this? How do we come up with the possible factors to check? So that's what we're going to be doing here for the next little bit, is talking about like finding that starting point. So one tool that we're going to use is called the rational zeros theorem. So what the rational zeros theorem says is, if we have some polynomial with leading coefficient a sub n and constant term a sub 0, then every possible, I'm sorry, not every, I should say, the only possible rational zeros for this polynomial are of the form p divided by q, where p is a factor of the constant term and q is a factor of the leading coefficient. So those would be the things that we'd want to check with our synthetic division. Let's do an example to kind of illustrate the point here. Okay. So it says make a list of every possible rational zero for the polynomial f of x equals 3x to the fourth plus 4x squared minus, or plus 7x minus 4. So I know that this is like my a sub n. This is like my a sub 0. So my p is coming from here, and my q is coming from there. So what are all the factors of -4? Someone tell me a factor of -4. 1, great. What else? 1 will be on every list for every set of factors, right? 2, yep. What else? 4, come on, guys, right? 4 divides itself. There's still 3 more that you're missing. If you see one of the 3 more, you'll get all 3 of them. Yeah, good. So they should all be plus or minuses, right? Because you can have positive or negative. The q is going to be all our factors of 3. What are our factors of 3? Still 2 more. Yeah. So can I have negatives of each of those? So far, so good? Okay. So my possible rational zeros are going to be 1 divided by 1, 2 divided by 1, 4 divided by, 1. So plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 4 over 1. And then 1 divided by 3, 2 divided by 3, and then 4 divided by 3. Everybody's okay with the complete list here that we've made? Now, in practice, I would just write that as plus or minus 1, plus or minus 2, plus or minus 4, right? There's no sense in being like weird about that. But in all reality, if these lists get long, like if you have a lot of factors of p and a lot of factors of q, doing this is like, enumerating this is like super annoying. So you are welcome to write that same list this way. Or you can just write the factors of p divided by the factors of q and just write as one big fraction like this with commas in between the stuff. That just means the same, you know, these two things mean the same thing. We're just going to, you know, if I have 6 things in my p list and 6 things in my q list, that's 36 fractions to list, which, whoa, boise, that's a pain in the tuchus, right? Just going to take up a lot of space, going to eat up a lot of time. We okay with how I came up with that list? Okay. So using the possible, or this rational zeros theorem, what I can do is I've now figured out, okay, So this list, well, let's maybe really write it this way, is a list of all the possible synthetic divisions that I might want to do. So what do we notice? How many divisions would be at most what I have to do before I found a factor? How many numbers are on that list? There's 12 of them, right? So maybe I'd have to do up to 12 synthetic divisions before I found one that gave me a zero remainder. Yeah. Can we do any better than that, Mr. Kulik? Well, yes, it's a lot easier to do better than that in your day. Now, back in my day, this following theorem was super useful. Less useful now for you because of the technology available to you that was not available to me as a high school student. So this next theorem says if f of x is a polynomial with a positive leading coefficient, and we divide by k using synthetic division, and really when we say, we really mean the factor x minus k, but whatever. If that k, so like x equals k, is positive, and every number on the bottom line of your synthetic division problem is non-negative, then k is an upper bound for all of the real zeros of f. And if k was a negative value, and every number in the bottom line alternates between non-negative and non-positive, then k is a lower bound for all the zeros in f. So when I did this, what you would do is you'd start with like, you know, like I'd go up here and I'd start with like -1 and +1 and do the synthetic division and see what I got there. If I got a 0, great. If I didn't, I'd look at this theorem to see, okay, does that eliminate, like, you know, if I find that 1 is an upper bound, great, then I can cross off 2 and 4 from my list. Or if I found that -1 was a lower bound, I could cross off -2 and -4 from my list, right? So it like would allow me to kind of do this synthetic divisions with these rational zeros, but I'd also like be able to discard or cross things off my list as I went that were now impossible, which was helpful. Now, you guys have a much better way of checking this than what I did. What tool do you have available to you as a student that Mr. Kulik would not have when he was back in high school in 1997 or something? The graphing calculator, yeah. So in practice, what you'll do is you'll just type the polynomial into your graphing calculator and look at the picture and see where the x-intercepts are. And that'll accomplish the same thing as this theorem without having to do any kind of guess and checking. But I'll ask you to do this in your homework, and I might ask you to do it on the test. So let's run through an example of how to use this theorem. Sound good to you guys? So it says, to show that every real zero of the polynomial f of x lies within the interval -5 to 4. So I'm just going to do 2 synthetic divisions, one with the beginning of my interval, and the other with the end of my interval. So for my first synthetic division, oh, that's not right. Mr. Kulik, 6 is not 1. You know, sometimes it's hard. Math is hard sometimes, you know? That's not right either. That's more like it. Okay. So if k is less than 0, that's what we have here. I want alternating between non-negative and non-positive. Did those alternate? Yup! So what that tells me then is -5 is a lower bound. Is everybody okay with what I did there? do the same synthetic divisions now. This time, my k is positive, so that bottom line, I want all to be non-negative. Yup, that worked. So I know 4 is an upper bound. So I know any rational zeros that I might want to use for synthetic division would have to be between -5 and +4. So anything on my list of possible rational zeros that was bigger than 4 or smaller than -5, I could discard immediately just from this analysis. Does that feel okay? It's something, right? All right. So let's do an example now of actually finding these zeros. All right. So, because this is degree 3 polynomial, I know I have at most 3 zeros, right? And then I'm going to go do my possible rational zeros. So it's going to be the factors of 30. Uh, 30 is, nope, not 4, but 5, 6, 15, 30. Over the factors of 6, 1, 2, 3, and 6. Everybody okay with how I did that piece? Now I'm going to go to my calculator. If you have your calculator with you, I invite you to take it out and turn it on, and you can follow along if you like. If you just want to sit and watch, that is okay as well. What I'm going to do is I'm going to go to the y equals menu, and I'm going to type in this polynomial that I'm interested in. And now I'm going to set a window. So from my possible rational zeros list, what is the smallest number on that list? Nope. Remember, we have negatives. Not -1, -30. What's the biggest number on that list? +30. So I'm going to use those as my x-min and my x-max. Now, all I'm really caring about is where the graph crosses the x-axis, because those will be the candidates for my zeros. So I'm just going to make my y-min and y-max -2 and +2. I just want to be able to see where it's crossing. And I want to see how it's crossing. Is it a bend, bounce, or straight? So once I've done that, I'm going to go ahead and hit graph. Take a look at what I see. So it looks like everything is happening between, say, like -6 and +3. Everybody agree with that? That's where all the crossing is happening. I'm just guessing. So I'm going to just reset my window there, narrow it down from instead of -30 to +30. I'll go from like -7 to +4. Just in case there's like a bend or a bounce, I want to be able to see what's happening on the other side of -6 and the other side of +3. So I want to give myself a little bit of room. So this looks like -6, and that looks like it's passing straight through. That looks like maybe +1/3, and that's passing straight through. And that looks like maybe 2.5, and that's passing straight through. Do you guys agree with my analysis of what I'm seeing in my picture? Okay, so I'm going to write that stuff down now. Oops, that was positive 1/3. Just do that. Everybody so far so good? What I'm going to do now that I've looked at my calculator is I'm going to check to see if -6 should be on my list of possible rational zeros. And I see it there. And then I'm going to check for positive 1/3. Is that on there? Yup. And then positive 5/2. Yup. So all three of these would be good candidates for starting my synthetic division because all of them are on my rational zeros list. Remember that not all real zeros are rational. You could have something with a square root in it. You will not be able to use synthetic division to find something with a square root in it. You'll have to find it using like a quadratic formula or something later on after we've done some factoring. So it's really important that you're checking to make sure that what you see in your picture is on your list of possible rational zeros. Is everybody cool? Here it looks like that's the case. If you had your choice, which one of these three numbers would you want to use to do synthetic division with? -6, positive 1/3, or positive 5/2? -6. Why is that? It's not a fraction, right? In addition, if I looked at my graph, I'm pretty darn sure, because there's a tick mark right there, that that's -6. Could this have been like, you know, instead of -1/3, could it have been just like -0.3? Sure, I estimated that, right? The same thing with this 2.5. Could have this been like 2.4? Sure, I just estimated it. You know, I don't know for sure that's what it is. Now, looking at this, I'm pretty confident that it's 2.5 because it's on the list. It's something close to it. But I'm still making an estimate. Like it's, you know, I don't know that for sure. Now, suppose it was just a choice between 2.5 and 1/3. Which one would I want to pick then? If I had a choice between 2.5 and 1/3, if those were just my two choices, which one would I want to pick there? Give me the 2.5, because when I do the synthetic division, I can just use the decimal. I don't have to use 5/2. I can skip having to do any fractions. The 1/3, I'd have to do fractions because I need that. I can't round a decimal to do the synthetic division. I can't use 0.3 repeating. That don't work. I have to like keep it as a fraction of 1/3 because the decimal is infinite. The 2.5 though, that decimal terminates. I can just treat that as a decimal. That makes the arithmetic way simpler because I don't have to muck around in fraction land. You know what I'm saying? So it's not a like one of these looks better than the other. It's the actual mechanics of doing the synthetic division is much easier if I can make it a decimal than if I have to keep it as a fraction. But we're not going to do either of those because -6 is the one A I'm most confident in, and then B is not a fraction. And it works. So before I move on, what I like to do here is I like to write down what exactly this synthetic division accomplished. So this was our starting problem. This synthetic division, because -6 gave me remainder 0, I know that x plus 6 is a factor. Everybody agree? The other factor then has to come from this. So reading from right to left, remainder constant x squared, and then just keeps going up 1 degree as you go to the right. So my other factor has to be 6x squared plus minus 13x, and then minus 5. Is everybody okay there? Now I can do one of two things. If I'm looking for zeros, I've now factored this into a linear piece and a quadratic piece, right? If I use the zero product property and set each of these two factors equal to 0, I can solve every linear piece. That's really easy. And I can use the quadratic formula to solve every quadratic piece. That's relatively easy. Alternatively, it would still be okay to continue doing a second synthetic division here and use like 2.5 or whatever at this point. I wouldn't do that. I would just set this equal to 0 and apply the zero product property, because I'm going to exit the synthetic division train as soon as possible. So reminder, the quadratic formula, if you don't remember that, for the polynomial ax squared plus bx plus c, the quadratic formula is negative b plus or minus the square root of b squared minus 4ac over 2a. Should you have that memorized? Yes. Every high school math student, by the time they graduate high school, should have the quadratic formula memorized. You should have used it enough that that just kind of happened. All right. Let's see. Negative 13 is 13. 13 squared is 169. 4 times 6 times negative 5. Oops. That was supposed to be a minus sign in there. Come on now. Yes, is 120. 169 plus 120 is 289. The square root of 289 is 17. You could do that all on your calculator if you wanted to. So 13 plus 17 is 30, divided by 12 is 5 over 2. 13 minus 17 is negative 4, and then over 12, that's negative 1/3. And you take those three together, 1, 2, 3 solutions, and we're good to go. Questions so far? Well, the question you should be asking is like, Mr. Kulik, those are just the x-intercepts from the graph, man. Like, why can't I just graph this and find the x-intercepts with my calculator, dude? Like, can't I just do that every single time? And like, yeah, okay, they're decimal approximations. They may not be exact values if there's a square root or something in there. But like, who gives a rip? Like, I got it. Here's the catch. All zeros aren't real numbers. You can also have complex or imaginary zeros, and you're never going to be able to find those just looking at the graph on your calculator. That's where we're going next. So section 3 or 13.4 says, okay, what if I have the possibility of getting complex or imaginary zeros? Well, right away, we're going to update that theorem from the previous section that told us that we have at most, the number of zeros is at most the degree of the polynomial. Well, this new theorem called the fundamental theorem of algebra says, no, 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 no. We can do better than that. That the number of solutions is the degree of the polynomial, provided we count real solutions, complex solutions, and multiplicities. So if a solution is used as a multiplicity of 3, it's used 3 times, then we count it as 3 separate solutions. But if we do those 3 things, we count the multiplicities and the imaginary, we have that the total number of solutions for the polynomial is the same as the degree. So this should tell us exactly when we're done, if we found them all. Everybody's cool? So that's helpful. The second piece is going to come from this, identifying these imaginary or complex solutions. So our theorem here is called the complex conjugate solution. So this says that if I have a polynomial, yes, sure. If I have a polynomial with real coefficients, and we have the solution, or a 0, a plus bi, I know automatically that I also have to have the conjugate 0, a minus bi. So our imaginary solutions are always going to come in conjugate pairs. So if I have a plus bi, I also have to have a minus bi and vice versa. So, for example, let's say we ask you to do the following. And we ask you to write a polynomial with the lowest degree possible that has the zeros 1, 3, I'm sorry, negative 3 and 1 plus I root 2. So we know that we have these 3 zeros, right? Now, I know, because of that complex conjugates theorem, I also have this 4th zero, the conjugate of 1 plus I root 2. Everybody's okay there? What I'm going to do is I'm going to change these zeros now into factors. So I'm just going to subtract 1 from both sides, subtract 3 from both sides, subtract 1 plus I root 2 from both sides, and subtract 1 minus I root 2 from both sides. Now, I like to take the complex number all as one big thing like this. You could subtract the 1 and then subtract the I root 2 separately. But I think doing it this way is going to be easier to kind of keep track of the negative signs and everything else. So my recommendation is to do it the way that I'm doing it. But acknowledge that you don't have to. And I'll show you where keeping the complex number just as one thing pays us some dividends in like simplifying what we have to do. All right. So now I've translated these 4 zeros into 4 factors, right? Now I'm going to multiply these 4 factors together. Everybody's okay there? Still doing okay? What I have now is a polynomial, right? Because I just have 4 polynomials multiplied together. The result should be a polynomial. Everybody agree? So to get this polynomial now, all I have to do is FOIL this thing out. My recommendation to you is to always FOIL the things that are in conjugate pairs. FOIL those things together first. And then anything else that's just like a regular old factor, whatever, you can FOIL together. So if I FOIL x minus 1 times x plus 3, I get x squared plus 2x minus 3. If I FOIL this together, the other piece, I'm going to do x times x. I'm going to do minus x times 1 minus I root 2. And then minus x times 1 plus I root 2. And then plus 1 plus I root 2 times 1 minus I root 2. Is everybody okay with how I FOILed that out? Now I'm going to distribute my negative x through. And then let's look at what we have here. Look at what I have here. That looks like a difference of 2 squares to me, right? I have an a plus b, or a plus b times an a minus b, right? Everybody see that? I know when I FOIL that out, I just get a squared minus b squared, right? So rather than FOILing this here, I'm just going to write it that way. Now you could FOIL that out and you'll get the same result. Things will cancel out, but like save yourself the grief. This is one of the advantages of kind of like keeping this all together like we've done, right? It just makes life a little bit easier to handle there. All right, so let's continue simplifying down. I notice I have a plus I root 2 and a minus I root 2. Those cancel out. And I have a negative x squared and another negative x squared. So that can become negative 2x. I'm sorry. I have a negative x and another negative x. Neither of them are squared. What's 1 squared? Come on, it's 1. 1 times 1. Goodness gracious, people. And then how do I do I root 2 squared? Well, remember when I square a product, that's going to be both factors squared. Do you guys recognize I squared as something? From algebra 2, you should remember that I squared is negative 1. And what's the square root of 2 squared? Come on, guys, it's just 2, right? So what do I have? I have x squared minus 2x, and I have 1 minus negative 1 times 2, so that's 1 plus 2, so that's going to be 3. Bring this guy down. And now I just need to FOIL this last bit out. So I have x to the 4th minus 2x cubed plus 3x squared plus 2x cubed minus 4x squared plus 6x minus 3x squared plus 6x minus 9. Combining stuff together, that's a 0, 3, negative 1, negative 4x squareds So we got rid of all those guys now. 6 and 6 is 12x, and then minus 9. Oh my God, Mr. Kulik, that was like the never-ending problem. That was like so excruciating. Here's the deal, though. When it comes test time, when I ask you to do this, that's enough. At that point, you've used all the theorems, you've given me the good answer. The rest of it is just like tedious algebra 1/2 foiling that just takes a bunch of time. I don't need you to take all that time. Like, it's a time test. Like, let's cut out the like really tedious, lengthy, like symbol pushing that shows me nothing other than whether you remember algebra 2 or not, and make more time for problems that I actually have been teaching you how to do. You know what I mean? So the skills from that point forward are all prior learning. I'm not so interested in assessing all of that. Although you should be able to do it. You should do it in the homework. But on the test, I would say that like once you've got it in a factored form, you can be done. You know what I say? You know what I mean? Oh, there's one other thing here. When it says lowest degree possible, why do I include that? Because if you were an insane person, and none of us are insane, I hope, technically speaking, you could do like, oh, I could make that one to the 3rd, I could make that one to the 5th, and this still has all the same zeros, right? It's still going to have, but like, why? Why would you like use that factor more than one time? All that means is like more foiling for you, right? So if we just use each factor the minimum number of times you need, that's how we know we're going to have the lowest degree possible. So like almost nothing do you have to do with that, right? If you just like act sensibly, your answer will have the lowest degree possible. Now, if you're an insane person and want to make the problem way harder than it needs to be, I don't know what to tell you. Like, stop doing that. Life is hard enough. Live simply. All right. Let's go on and now look at a finding the zeros problem that involves possibly imaginary / complex solutions. All right, I start. Fundamental theorem of algebra tells me how many solutions should I have? Or zeros? I have exactly 3 zeros, right? Everybody's good? My rational zeros theorem tells me that my list of possible rational zeros is going to be the factors of 36. Oh, dear God. Make sure I get them all. There's like 100,000 of them. Over the factors of, well, at least that's 1. This is why there's 60 seconds in an hour, is because there's so many divisors of 60. That's why we chose 60 seconds in an hour, because it's like easy to subdivide it a bunch of different ways. As opposed to 10, where there's only like a couple of divisors of 10. There's so many divisors of 60. That's why that number was chosen. Yeah, it's interesting, right? And we go to our calculator. So let's type this in. Clear that out of there. X cubed plus 4x squared plus 9x plus 36. I'm going to reset my window from negative 36 to positive 36. Hit graph, take a look. Looks like I have 1 0 that I can see there at like -3 maybe. So I'll just change that from like, I don't know, -6 to 0 or something. Oh, it was at -4. And that's going straight through, right? So that's one solution there. Where are the other two, though? We're supposed to have 3 total. The other 2 must be imaginary, right? I have one real solution, the -4. The other 2 must be imaginary, and that's good because the complex conjugates theorem tells me that those imaginary solutions always occur in pairs. So if I I can have 2 of them, 4 of them, 6 of them, but I'm not going to have 5 of them unless I have an I as one of my coefficients, and you're never going to see that in this class. So to start my synthetic division, which one am I going to choose? Well, I only have one choice. It's got to be the -4. So there's my synthetic division. What was my remainder? 0. Yay, 0. So far, so good. What that polynomial or what that synthetic division tells me then is that one of my factors is x plus 4. Again, I'm getting that because -4 gave me a remainder 0. And my other factor has to be x squared plus 9. I get that from those numbers there. So far, so good. Now, x squared plus 9 is a quadratic. To solve that, I can always solve that by using the quadratic formula. So at this point, I'm going to exit the synthetic division train and solve this quadratic. Now, x squared plus 9, do I really need to use the quadratic formula to solve that? No, I'm just going to do it directly, right? It's just going to be just a little bit simpler. Square root both sides. When I square root both sides of an equation, don't forget your plus or minus. When I square root a negative, what do I get? I get an I, and the square root of 9 is 3. So that's one real solution here, and this is 2 imaginary there. The 2 is for plus 3i, and the second one is minus 3i. Everybody okay there? Okay. Let's do one more example, and we'll be done for today. Sound good to you guys? Probably. You look bored as all dickens. I'm trying to be entertaining, and not belabor the point too badly on these things, but I get it. You've been sitting here for a while. All right. So find all the zeros for this polynomial. Okay. Oops. Oh, come on now. Nobody wants this. Hide this stupid button. Oh my God, I pressed it again. Okay. How many zeros should I have? 4 zeros. How'd you get it, Lexi? The degree is 4. Excellent. My list of possible rational zeros is the next thing I do. So those should be the factors of what over what? The factors of what number divided by the factors of what number? Factors of 35 over the factors of 8. Everybody's okay? Next, what do we do? Go to my calculator, analyze what I see going on. I can learn so much just by looking at the graph. Okay, So got that typed in. I'll change my window from -35 to +35. Again, the biggest and smallest zero on my possible rational zeros list. Hit graph, take a look at what's going on. Ew, Boise, everything looks like it's real close to zero there, so maybe I'll just reset my window to go from like -2 to +2. That probably captures all of it. Hit the graph again, take a look. Okay, so this looks like a half, right? That's the 1, right? That's x equals 1. That looks like a half. You guys buy that? What does this one look like? Give me a guess. -1.1. I would guess probably if I looked at my thingy here, I see that I have +1/2, right? And what's going to be close to 1? Well, that's probably 5/4. That's 1 1/4. That's what I'm going to guess that probably is. Everybody's okay there? Again, you're just taking a guess. I'm going to see if that guess is something close to something on my close to something on my list. Both of those are straights, so I have 2 real solutions, but I'm supposed to have 4. Where are the other 2? They got to be imaginary. The only way I'm going to get those is using the quadratic formula, so let's start our synthetic division here. Which one would you want to start with, a half or -5/4? I mean, give me a half, I guess. They both are kind of El Stinko'd. But I guess a half is probably easier. Yay! So I have x minus 0.5 times 8x cubed minus 22x squared plus 16x plus 70. Ugh, what a bummer. Look at this. Can I do anything with that? I don't know how to factor that, right? That's not quadratic. What am I going to do there? Well, I got no choice. I'm just going to do a second synthetic division with my other 0. Notice I'm doing it on the result of the previous synthetic division problem. So that is -10. And that's +40. That's -70. Yes. So now I have x minus 0.05 times x plus 1.25 times 8x squared minus 32x plus 56. I'll set that equal to 0. But before I go and start applying the quadratic formula, what do you notice in here? I noticed something kind of good. Look at the coefficients. Yeah, there's greatest common factor of 8 in there. I'm going to take that out. I'm going to put 4 of it in there and 2 in there. And now when I apply the zero product property, I have x equals 1/2, x equals -5/4, x equals 4 plus or minus 4 squared minus 4 times 1 times 7, which is 28, over 2 times 1. 16 minus 28 is negative 12. That's going to be 2I root 3. And that reduces to 2 plus or minus I root 3. So those are my 2 imaginary. And these guys are my 2 real. And I'm done. Woo! That was a workout there, folks. So for next time, you guys should work on 13 through 14. And then really 20 all the way to the end. For your virtual day on Friday, what should you do? Work on this. Or the Delta Math if you haven't finished that. That's your Delta or your virtual day assignment. The Delta Math is you worked on last class, yes. So you probably have that done. Or close to it. Also, next class should expect home, work, whiz. Really on the first lesson that we did. Nothing from today. Coolio? Questions for me? Okay, let's stop. I'm tired. Are you tired? Exhausted. It's exciting, but exhausted.